Now we're going to introduce methods of proofs. Well, the very first method of proofs that we're going to learn is how to use the definition to directly prove some statements. So this is direct proof using definition. Okay, using definition. So to apply this method, we're going to have the very first category of the contents that we're going to cover, which are numbers, prime numbers, and composite numbers. Then we're going to move on to divisibility. Definition. How do we define a prime number? How do we define a composite number? So let's see. An integer like n is prime if and only if it satisfies the following condition. First of all, your n must be larger than 1. It's a common mistake that student thinks n equals to 1 is a prime number. N must be larger than 1. This is your first condition. The second condition, and for all positive integers, like what? Let us use R and S. If n is the product of R and S, then you can conclude that n is equal to R or n is equal to S. Methods of proof. Direct proof using definition. The very first category is prime and composite numbers. So first we define a prime number. An integer like n is called a prime number if and only if it satisfies two conditions. The number must be larger than 1. If the number is the product of two other numbers, one of them is definitely 1. When we say n equals to R, n equals to S, it means that one of these is eventually equal to 1. Otherwise, we say that, hey, that number is composite number, or officially we write it this way. Definition of a composite number. An integer like n is called composite if and only if, again, n is larger than 1, and if n is equal to R times S, R is bounded between 1 and n. There is no way R is equal to 1. Also, S is bounded between 1 and n. There is no way that S is equal to 1 as well. So compare these two definitions. The composite number is larger than 1. If it's a multiplication of two numbers, then for sure you can say that, hey, these two factors are larger than 1 and smaller than the integer itself. So these are the factors. these are the official definitions. Now let's go over some examples. The very first one is 1 a prime number? Let us go back to the definition. To check to see if 1 is a prime number, we are looking at the definition up here. A number is prime if and only if it's larger than 1. So it doesn't satisfy the very first definition, the very first part of the definition. This is just 1. Okay. So the answer is no. 1 is not a prime number, definitely. B, is every integer greater than 1 either prime or composite? The answer is definitely yes. We just define prime numbers for any number larger than 1, multiplication of R and S, n is R or n is S, any number, any integer larger than 1, the multiplication of R and S, and you have 2 factors that are not equal to 1. So the answer is definitely yes. So being prime, being composite, it helps us to categorize the numbers into 2 categories. See, right? The first 6 prime and composite numbers. Okay, very good. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and the rest of the numbers. 2 is prime. We all know that. 3 is prime. 5 is prime. 7 is prime. 11 is prime. 13 is prime. The rest of them are composite. Composite, composite, 8 is composite, 9 is composite, 10 is composite, 12 is composite, and we can just categorize the rest of the numbers that we have.